Alright, good afternoon. Let's start the lecture. Okay, so in previous lecture we finished this Z transform. Okay, so the very basic expectation is how to obtain a Z transform for simple, basically typical type of functions, and how to obtain inverse Z transform using partial fraction expansion, corresponding to three different cases, right? So that's the previous lectures. Okay, so now today we're going to continue here. The ultimate objective for today's lecture and also next lecture is about deriving the so-called pulse transfer function. Okay. So for continuous system, basically you have a Laplace transfer function for any closed system or open loop system, right? So we wanted to obtain the transfer function representing the system. And for discrete system, we want to do the similar things. So we obtain, instead of just this time, instead of calling transfer function, it's called pulse transfer function. So you actually will see why it's called pulse transfer function. In order to do that, we have to explain two concepts here first. Okay, the first concept we want to explain is the so-called impulse sampling. So let's look at the concept impulse sampling first, and then we'll look at another concept called the zero order hold. So, and then we'll look at how do we derive for pulse transfer function. Okay. First of all, impulse sampling. The whole idea of a discrete system is about sampling. Basically, starts from sampling. And if you have a system, you have a signal x of t, and here is a sampler. So this is what we call, it's a real sampler. So real sampler basically is what happens in reality, right? If you put a sampling, and you sample this signal here, and we get basically a whole bunch of basically a sequence of numbers here out of the sampling here. Okay, yeah, and we call it x of k. So that's basically the sampling process. Okay, but in order to put it into mathematical theory, so we don't use just the description, we have to come up with a so-called math model here. So what's the mathematical model for this process here? Okay. So this side, for the mathematical modeling, this side is still the same, so you have your x of t at here. Okay. Yeah. And then the real sampler, okay, the real sampler is modeled, okay, with a so-called impulse sampler here. Okay. So the impulse sampler basically is sampling time t, so we use this symbol delta t, okay, to represent this impulse sampler or this real sampler at here. Okay, yeah. What's the difference? You'll see the difference. Basically, you pass this continuous signal through this impulse sampler, okay, and once they pass through this impulse sampler, it generates. What it generates is a sequence of impulse signals. So that's what coming out of this impulse sampler at here. Okay, impulse sampler. The other difference is this guy here. Okay, this is a time function, and what comes out of this impulse sampler theoretically, okay, mathematically. So we use x star of t, okay, to represent the results, okay, coming out of the impulse sampler, and this is technically, this is still a time function. Okay, so this is still a time function. It's a broken time function at here. Okay, yeah. Now for each one of the impulses, right? Impulses, you can always, for example, you can always represent each one of these. For example, the first one, you can call this is x naught time delta naught. Okay, so this is an impulse. That's the direct. This guy here is a direct delta signal. Huh? Yeah. So this guy here, this is the direct delta. So if you recall the direct delta, basically at t equal to 0, and then it's infinite, right? But there is a property, if you recall, that for direct delta, when you integrate from negative infinite to positive infinite for this direct delta, it is equal to 1. Okay, it's equal to 1. So the x naught at here basically represents the magnitude of this direct delta at here. Same thing if you look at the second one here, and that will be basically x1 at delta t minus basically capital T sampling time, right? And correspondingly you can write down for the rest of them. So that's basically what the x star of t is. It's essentially, it consists of infinite number of impulses at here. Okay, yeah. So that's the mathematical model for this sampling process at here. So if I summarize for this process at here, so basically we use arrow sign at here representing this impulse sampler. That's to differentiate between a real sampler here. Okay. Here is your delta t. This is your impulse sampler. Input is x of t, and output is x star of t. Okay, yeah. And of course, your input will have a Laplace transform x of s, and output, right? Same thing. Remember, this is still basically a time function here. Okay, it's just a very broken time function. So this one here, you could have basically x star of s at here. Okay, so we're going to actually talk about this. There's a new operation called the start Laplace transform. Okay, so there's a connection. Essentially, there's a connection between this x of s and the x star of s. Okay, so we'll look at that shortly. So let's basically, this one here is the model for this process. Now let's go back to this x star of t at here. Okay, let's go back to the x star of t. Okay, let's look at explicitly what is the x star of t, right? Yeah, because we need to obtain the x star of s from x star of t. So let's write down the x star of t at here. So you can see x star of t is consists of an infinite number of basically impulses at here. So you can literally just say, okay, x star of t is the addition of all of the impulses, right? Now the first one is x naught delta 0. Okay, so x naught delta 0, you can actually this is not 0. This is a t at here, delta t. Okay, yeah. So delta t is when t equal to 0, it exists only at here, so that's okay, right? Yeah. Yeah, this is delta t here. And then the second one is x1 and delta t minus capital T. So shift it to the right by 1 sampling time, and then you can just keep writing a few more at here, right? So that's your x star of t, right? X star of t. So let's put this x star of t into one single expression, okay, as a summation sign at here. So here is x of k capital T and delta t minus kt. So that's your x star of t. Okay. Is it good? So far so good? Yes.
Are you missing like a t between the x of kt, but then the summation 0, 1, 2?
Am I missing a t?
Like see how there's a t there?
Where?
So x of kt just to the left, shows kt.
Oh, this kt here?
But then above it's just x of 0 is the line.
Yeah. I can literally write, just remember in the previous lecture we mentioned you could write x of kt, or and often in time, depends on how you look at these things, right? So if you look, okay, here's my x of t, and then I got x of kt, right? But if you completely disregard this x of t, you just look at this sequence of numbers here, and this is basically what x of k, right? Yeah. So in a lot of senses, these two you can consider they're equivalent. Okay. Yeah. So in terms of the Z transform or discrete analysis, it cares about the information sampling t, but if you're only given is a sequence numbers, then that's basically x of k, right? Yeah. So it doesn't contradict to these two at here, right? It doesn't contradict. So you could just write x of k at here. That's fine. Okay. Okay. So that's x star of t here, right? Yeah. Now if I look at the model here, for x of t, I can always do a Laplace transform, get x of s. So literally, I can do the same thing. Then I will say, okay, so what's the Laplace transform x star of t, so that I can get capital X star of s, right? So let's try this one here now. So basically, let's look at what is Laplace transform of x star of t at here. Okay. Yeah. And the results, I'll call it capital X star of s. Okay. So to apply the Laplace transform in here, so we are basically applying Laplace transform to each one of the terms at here, right? Each one of the terms. Okay. We do need to make use of one property for Laplace transform. Then, if you recall that, when you take basically Laplace transform, for example, this delta t, okay, yeah. If you just take Laplace transform delta t, I don't know if you remember, what is that? It's just what? 1, right? So if you take Laplace transform of delta t minus capital T, basically it's a delayed signal here, right? It's a delayed signal. And what you get is just e to the power of a capital T times s, and then time the original Laplace transform. In this case, which is 1. So if you take a Laplace transform delayed, okay, delta function, and you get this one here. All right? Yeah. Same thing if you apply Laplace transform to this one. This is delayed by 2t. Then that's negative 2ts. Okay? Yeah. So we use that property at here. Then for the first one here, Laplace transform for the first one, okay, that's just the constant x naught. So and Laplace transform is 1, so just x naught in here, right? And then plus Laplace transform this, and that's x1 times this. And Laplace transform this term, x2 of this, right? Okay, and they can keep adding things up. Okay? Yeah. So this is a Laplace transform for x star of t, okay, to get x star of s, and I can rewrite this one into the summation signs, so using the summation symbol. So here's your x star of s. Okay, x star of s. Okay, so let's observe this x star of s, right? Yeah, let's observe this star of s. The first impression maybe it's not that clear, but I want you to do a substitution in here. So let's say if you substitute this e to the power of a ts with the symbol z. Okay, so substitute this e to the power of ts with the symbol ts. Basically, for this term in here, right? For this term, and it can be written as e to the power of a ts to the power of a negative k. Right? So exponential function. Okay? So if I substitute this e to the power of ts with z, okay, which means what? Which means for the basically for this side here, for the left side here, right? For the left side here, the s. So here is et, so that meaning what? S is equal to 1 over t ln z, right? 1 over t ln z. So for the left side of it here, we're doing a substitution with s equal to 1 over t ln z, right? Yeah, ln z. And then the right side, you replace that e to the power ts with z, and that gives us what? Z to the power negative k, right? Negative k here. Okay. So that's the results of this substitution. Okay. So once you have this one now, and if you look at the right side, and what is the right side here? That's basically the Z transform, right? So this is your Z transform for x of t or x of k. Okay? Yeah. Or we literally we write capital X of Z, right? We can write capital X of Z here. Okay? Yeah. So yes.
What are you doing with that s equals 1 over t ln z?
What do I do with this part? So you can take ln both sides, right? If you take a ln both sides, then this becomes ts.
Right,
Yeah.
sorry.
Yeah. So essentially, I rewrite this one into as s into equal to the z term. Okay. So what this one here is a very important result set here. What it tells you, okay, from the result set here. So what it tells you here is you have your x of z, which we all know what it means. You know, we're taking z transform, right? So and now you can literally see where is this x of z from? This x of z, you can see it comes from a substitution for the x star of s by substitute this s with 1 over capital T ln z. That makes sense, right? So that's basically a different information we get. You know, we have the traditional z transform, and now we have a new information. We say, okay, so x of z, you could also obtain the x of z from where? From x star of s by substituting the s with this one here. That makes sense, right? So let me write it maybe here. Could be obtained from x star of s, okay, by letting s equal to 1 over t ln z. Okay. So immediately you can think, if I do the z transform, I can do the traditional one, you know, to get the x of k, and then do the z transform by applying the formula. Or somehow, if I can get x star of s, then I can do this substitution. I can still get the same x of z, right? Yeah. Now, equivalently, you could also see is this x of z, okay, signifies x star of s. Okay. The pitfall here is, okay, often in time from here we remember one very important relationship between the Laplace s and the z transform z, which is this information, s equal to 1 over t ln z. Okay, that's a very important connection, okay, between the s and the z. Okay, but the pitfall here is, when do we use this substitution? Right? When do we use the substitution? You only use it for this x star of s. Okay, you use it on x star of s, and not what? Not the x of s. Okay, yeah. Is that clear? So because there is a pitfall here, and I remember when I was learning it, and when the teacher says, oh, s equal to 1 over t ln z, beautiful. So next time I just substitute s to here with that to get x of z, but that's wrong, right? Yeah, that's a pitfall here. You only do the substitution for the x star of s, not x of s. Okay, because this is a pair basically, okay, not this and that. So your x of z But we do have writings, basically from previous lecture saying x of z equal to z transform of this, or z transform of that, or you can write z transform of that. So they're all equivalent, right? Behind the saying and here, they're all equivalent. Okay, so that's fine, right? But doesn't mean that here, when you look at this as a new formula, and you can simply substitute s with this over here to get the z transform. Okay, yeah, so that's a very common pitfall here. That's the first information. Okay, second information, we'll come back to this information later here. Okay, basically, if you look at the model right here, x star of s. So x star of s comes from by passing this x of s through this impulse sampler, right? You pass this through this, you get x star of s. So, or you pass x of t through this to get x star of t. Okay? So there's a connection between this x of s and x star of s. There's a connection. So I'll write down the connection right here. As a matter of fact, I won't give a proof. There is a very lengthy proof in the textbook. I'll come back to this expression, okay? Yeah. So your x star of s, okay? Your x star of s is connected to the x of s by this formula here. Okay, by this formula. So here's the connection between the x of s and x star of s. Okay. Okay. So what the symbol here, this omega s. Okay, this one here. This is your sampling frequency. So your 2 pi over the sampling time, capital T, will give you this omega s at here. Okay, omega s. Yeah. And k, of course, just the time is varying numbers at here, right? And T is a capital. T is the sampling time. Okay. Yeah. Okay. So this is actually a fairly important expression at here. It explains a very important phenomena actually. Okay, if you start with basically if you recall that, right, this is what happens at here, right? So this is the process at here, right? This is the process. So if I start from the left side at here, okay. Now basically, if you substitute s with j omega, and let's turn it into a typical frequency analysis, right? Yeah, typical frequency analysis. In the control system, whenever you have a Laplace transform and you substitute s with j omega, you're doing frequency response basically. Okay. Yeah. So for frequency response, and there are two information. One is basically the amplitude plot, and then also the phase plot. So you can always plot the amplitude of this signal or this system right here. Okay. So here's x of s. So you could always plot this amplitude, or which is part of the body plot. Now, let's say I'll just use this bump right here to represent this frequency response of this system right here. Okay. Every system, there will be a bandwidth. So this could be the bandwidth of this system right here, or this signal right here, right? So that's this side here. This is what you started with, right? You start with this, and with this frequency plot, and passing this through this impulse sampler, or passing it through a sampling process. So then what's going to be at the output side then? So here is the expression right here. Okay, without giving you the proof, as I said, the lecture notes, the textbook doesn't have a proof there. So here is what's coming out of here. If you look at what's coming out of here, basically, if you look at this one here, It's this x star of s is what? It's addition of x of s, and then at g omega s, at 2g omega s, at 3g omega s, right? And if you let the k equal to 0, this is basically 1 over t x of s. So I could do the same thing for the body plot, right? So replace the s with g omega, okay? Then when k equal to 0, and here is your basically your x of g omega, of course, and then divided by capital T, right? Divided by capital T. Okay, so literally the magnitude should be lower now, okay, or should be higher, depends on the value of the t. Okay, but at k equal to 0, you have this guy here, right? You have this guy, okay, and then you can let's keep going. At the k equal to 1, what is it? It's x of g omega plus g omega s. Makes sense, right? Which is the x g omega plus g omega. Basically, you shift this guy either to the left or to the right, right? Depends on the k value, right? So you basically you get a whole bunch of bumps, right? For x star of s at here. That makes sense, right? So here's still your this is still your the bandwidth of the system here. And for two adjacent values here, okay, so this one here, this is your omega s. So this is how you shift, right? So this side here is negative omega s. So how you shift to the left and to the right by shifting the whole bump, right? Okay. So what's important at here is this. Now, the important part is the value of this omega s, or the value of the sampling frequency, determines how you shift this one, right? How much you shift this one to the left or to the right. That makes sense? So imagine this, right? So right now, the way I sketch is I don't have any overlap between the two adjacent bumps, right? But if your omega s is not big enough, your omega s is small enough, so your next bump maybe it's this. Does that make sense? Right? So basically you have an overlap between the first bump and then the second bump at here. Okay? Yeah. So what's so serious about that then? Because when you have a bump like this, then you basically when you put things together, it's like this adding this now, right? So your overall curve from here to here is like you added something at here. Okay? Yeah.
Is that like intersymbol?
There's a phenomena at here. There's a term for this. I'll show you. What is it? Aliasing. Exactly. Right. That's the phenomena called aliasing. Okay. Yeah. So you have the information. So information theory is actually, maybe let's first talk about information theory. What's the fundamental theory when you deal with information? It's called Shannon's theory, right? And Shannon's theory states that the sampling time omega s has to be how much? 2 times the system bandwidth, right? Yeah. In order for you to backward basically extract the information out for the original system here. Okay? Yeah. So I know this is a little bit too much for mechanical, but think about this, right? You know, you do a sampling with respect to the original signal, and you get a whole bunch of outputs at here, right? But there is a very good chance that you may ask it. So I do the sampling and get the output, and you say, okay, can I reconstruct the original signal based on the output here, right? Reconstruct basically means what is exactly the original signal here, right? What's the exact information? That's where the Shannon theory comes to picture here. So your omega s needs to be at least twice as much as the original bandwidth of the system in here. So omega 1 is the bandwidth. Okay. At least to be twice as much, there are two omega 1 there, in order to reconstruct the original signal. Okay. So why is that the omega s has to be at least twice as much omega 1 so that you can reconstruct here? Because if you look at the drawing at here, right? So let me erase this part here. So if I look at the drawing at here, if I want to backward reconstruct the original signal, what I could do is I could apply a so-called, basically, a low-pass filter, right, to apply it to this x star of s at here. So I get exactly the same shape, right, as the original x of t here. So that's fine. I can get the information what existed previously. Okay. But if your omega s is less than 2 omega 1, so that's basically the overlap phenomena, right? Then you have basically something here, here, and then you apply low pass. That's not exactly the same as the previous frequency response anymore, right? So you can't do that anymore. Okay, yeah. So this is an important part. Just this simple expression in here. Actually, yeah. Good. So that expression can explain this simple phenomenon here. Okay, yeah. There is a sequence of operation you can basically do. Okay, for example, you can apply a fast Fourier transform to obtain this x star of j omega, and then if you apply a low pass filter, you could get, okay, depends on the sampling time, you could get your x of j omega, and then if you do a inverse fast Fourier transform, and you can literally get back to this x of t. Okay, yeah. So that's this connection at here. Okay, between x of t, x star of t, x of s, and the capital X of s at here. Okay. So actually, I'm probably going to come back to the expression again here. Okay, the expression. This expression, I would encourage you to look at the page 146 in our textbook. There are probably a few pages of proof for that expression. Okay, yeah. So you can take a look at that if you're interested. Okay. Okay. That is the first concept. Okay, impulse sampling. Okay, impulse sampling here. Let's look at the second concept, zero order hold. Okay. Zero order hold at here. Zero order hold is a concept, and I think I covered in the first lecture when I explained the structure of a typical digital control system. So when you have a digital controller, by implementing some sort of a digital control algorithm, and you will come up with a digital control signal, maybe corresponding to certain voltage, and you're going to have to basically apply this back to the real system, right? In order to apply back to the real system, you can't directly apply this because it's discrete one. So we had to let it go through a certain type of holding mechanism. And zero order hold is the simplest type of holding mechanism, okay, to realize basically the digital to continuous conversion, right? So here's the illustration at here. If you have x of t, if I use this sampler as the simplest digital control, there's actually no control here. You just sample it, and you can let it pass through this zero order hold again, and you come up with some kind of a continuous signal now, right? So signal-wise, essentially, here's your input at here, and after sampler, you have a bunch of discrete signals here, and then with zero order hold, okay, basically you get some kind of staired type of input, but it's continuous, right? So this is discontinuous, but this is continuous here. Okay, yeah. Okay, so that's what from here to here. Okay, that is basically what zero order hold is doing at here. Okay, zero order hold, and this is a very important block for digital control. Very often you will have, for example, okay, you will have a system, for example, okay, connected behind this zero order hold, right? And this is basically going to be a part of a bigger picture of the whole closed loop system, open loop system, right? So the zero order hold is an important basically block, okay, in this digital control system. So what we wanted to do now is basically we want to not just know that how it operates, but also come up with a mathematical model. Okay, in this case, we want to try to come up with a Laplace transfer function representing this zero order hold. Okay, yeah. So basically, I need a mathematical model right here. Here's your impulse sampler. Here, let's say I wanted to derive a Laplace transfer function or S function corresponding to this zero order hold at here. Okay. So this is the idea at here. How do we derive a S function for the zero order hold? Okay, so I'm gonna rewrite something we just learned. Basically this part is the impulse sampling, right? And then here is your mathematical representation, okay, which is what we're trying to do. And here we got our output at here. Okay. Yeah. Okay. So for any block that you wanted to derive a S function or Laplace transfer function for this block, and what you always look at is always the input and output, right? And that's basically we wanted to do it here. Yeah. So let's look at this symbol here for the input, right? For the input at here, let's assuming a very simple input for this case. Let's assume the input is a delta t, for example. Okay, assume the input is an impulse at here. Okay, impulse. So if that's the case, then after the impulse passing through the impulse sampler, so this side here, right, the arrow pointing this location, pointing by the arrow, okay, there's actually nothing else but an impulse, right? Yeah, at this location. And for direct delta, okay, has a magnitude of 1. So that's your impulse at here, your x star of t. That's nothing. It's basically just this one here. Okay, just this. Yeah. So let's call this temporarily call this xi of here. Let's call it xi here. Okay, yeah, instead of x star of t. Now, what comes out of this? Zero order hold is what? What comes out of the zero order hold? Okay, so you have the zero order hold at here. So basically, you pass this one through the zero order hold. And zero order hold, all it does is it will hold the input by how long? Yeah, by the sampling time t, right? Yeah, and because this just only one signal here, so let's just hold it for one sampling t and then back to 0, right? Yeah. That's essentially what happens at here for the output. Okay, so let's temporarily call this as x naught. Okay, yeah, so here's xi and then here's xo. So here's input xi, output xo, which is this. Okay, yeah. And for the xo of t, okay, in order to do a Laplace transform, so this essentially is a rectangle signal which is equal to 1 between 0 and capital T, and then outside that it's all 0. So I can actually rewrite this one, okay, using the unit step signal. So I can let it, basically this is equal to u of t minus u of t minus t. So this essentially is like this, right? What's u of t? Here's your u of t, right? Unit step input. What's u of t minus t? It's this, right? It's this. So you use the first one minus the second one, and then you're left with just this rectangle box right here. Okay? Yeah. So now I have my input, I have my output, okay, for this zero order hold. Then I can derive my transfer function now by looking at is the ratio between the output signal and the input signal, right? Yeah, that's how you derive Laplace transfer function. Okay? Yeah. So the input is easy, that's just direct delta, so which is 1, right? It's Laplace transform. The output is XO of S, which is this guy here, okay? The u of t minus u of t minus. Laplace transform for u of t is, if you recall, 1 over s, right? And then here is a Laplace transform of a delayed unit step function by capital T. So Laplace, apply that shifting theory. Basically, I think we did that. We apply the shifting theory to this, right? When you apply a shifting theory, essentially here you have a e to the power of a t negative ts. Okay, that's because delayed only by capital T. Then time 1 over s. Okay. So that's your overall. That's the GH naught s, which is the zero order hold. A little bit simplification, you get y minus e to the power negative ts over s. Okay, yeah. There. This is your mathematical expression or Laplace transform for the zero order hold at here. Okay, zero order hold.
Could you also do this if you use a gate function instead of a 2-unit step function?
You could, but I think it's probably a little more complicated than by doing comparison at here. Yeah. In my lecture notes, I actually provided another method to derive this expression at here. Okay, and that method is using, I think it's using, I don't remember now. I think it's using this kind of expression at here. Okay, yeah. I think that this is a lot more easier to understand. In the future, this is essentially all you need to remember. So this is the expression representing a zero order hold block. Okay. Yeah. Okay. So that is zero order hold at here, right? That's zero order hold. Okay. All right. So let's continue the third concept, and which is now we're coming to the actual topic now, pulse transfer function. Okay, and I often just call it PTF. Okay, so how do we derive a pulse transfer function? Okay, yeah. Okay, so what is a pulse transfer function, right? Maybe let's give you a very simple example here. It's basically a concept of transfer function. Okay, so let's say your starting point is here. Your starting point is you were given, let's say, a difference equation. Suppose you were given it's a difference equation here. So you have your input u, and then you have your output x, and the u is given to a certain discrete system, and then output is the x, x of it's the output of the discrete system, okay? And overall there's a connection by this expression right here, okay? Yeah, and very much like a differential equation, right? Ordinary differential equation, okay? And you have an input output you get basically described by a differential equation. So in the continuous case, you know, you basically say what's the Laplace transfer function. But then in here, basically what we really care about is what's the so-called basically pulse transfer function at here. So all you need to do is you take a Z transform of both sides of this expression at here, okay? And we know that this as terms get x of z. Here you get a delay at here, okay? Basically multiplying z to the power -1. And here you get 2 delays. Okay. Yeah, that's the results, right? And then you derive basically a connection between output and the input, okay? And here you get 4. Okay, yeah. Now this is basically an example of this so-called pulse transfer function. Okay, but this is actually easy one because there's nothing else. The starting point is already discrete on both ends, right? So this one here, but what's written at the end here? This is an example of what we would call the pulse transfer function. Okay, yeah. So this is the counterpart of the Laplace transfer function for a system here. Okay. However, for actual system, okay, for some most of the cases, it's not as simple as this to derive a pulse transfer function. And a lot of the time, your starting point, okay, is something like this. So you have a so-called data sample system. Okay, so let's see. This is a diagram basically I showed you at the in the first lecture. I'm drawing. Let's see. I'm drawing a closed loop system here. Okay. Right. Here's a simple diagram, basically, that we have seen before. Okay, so reference input at here, and then output at here, for example. Okay. Yeah. So we call this is a data sample system. Now the reason is because if you look at this simple system here, if you look at the signal at different locations, right? If you look at the signals different locations, and you can see that this system, it's a system containing a mixture of signals at here, right? So here's continuous, and then here's a discrete. Right? So there's basically a mixture of systems at here. So this is why it's called. So there's a mixture system, mixed signals. Okay, there's a mix of signals here. Okay. So that's why this is relatively more complicated than just one single difference equation, okay, for you to derive a pulse transfer function, right? Yeah. So this is actually what we wanted to ultimately derive. If I'm giving something like this, then what will be a pulse transfer function, right? Okay. Yeah. So let's start from simple blocks. Okay, not a closed loop block like this. Let's start from very simple block. So simple block here, this is a simple block. Okay. Okay. So let's see. We're looking at this block right here. Okay. Yeah. That's a very simple one. You know, just basically consisting one impulse sampler and then one continuous block h of s. So this block right here, it could be a combination of two blocks. Basically, there's a zero order hold right here, and then there's a plant right here. So you basically combine. You could combine two blocks, okay, together. You can multiply this together, and then you get one single H block right here, right? Yeah. So either way, let's look at this one here, right? Here is your input x of t, okay, and here is your impulse sampler, and the 0, here is your x star of t at here. So let me write this on the top of it here, okay. And then output, let's call the output y of t at here. Okay, so that's consistently on the top of it here. It's all continuous. It's all in time functions. Time function, time function, time function. Right? Yeah. Now at the bottom here, I can write x, capital X of s, capital X star of s, and then here you have a y of s. Right? You have y of s here. Okay. So for pulse transfer function, right? If I look at this pulse transfer function here, pulse transfer function, it's about the ratio between two discrete signals, right? So ratio between the U, which is discrete, and the output x. Okay. So pulse transfer function is about the relationship between two sequences of discrete signals. So let's be clear about that. Okay. So PTF, okay, is about the ratio between two discrete signals or functions. Okay, doesn't matter. Okay. So that's what PTF is about. Now if I look at this one here, this is exactly what I call this a mix of signals here, right? It's a mixed signals here. So if I want to derive a pulse transfer function, the discrete signal here is one discrete, right? So the signal here is a digital signal, okay? Now here, there's no digital signal, right? Output is continuous here. But we can do this. Let's add some kind of a, this doesn't have to exist. So I call it fictitious impulse sampler. So then you get basically your y star of t or y star of s. Okay? Yeah. So this guy here, let's call it just basically a fictitious. It doesn't have to physically. This one here, you see, it has to physically exist, right? It's part of the control system. Okay? But this one here, when you're doing actual control, I have my signal given to the actual system and look at the system output. I don't need to do anything at all now, right? Because I already have the system output. Okay, so I don't need to physically add another impulse sampler to obtain this. So you could also use software to generate a sequence of numbers here. So that one here doesn't have to physically exist. All right? Yeah. But by adding this one, and now what we can literally see is, you see, okay, so I got one and here and one and here. So if I need to derive the pulse transfer function, then I just need to look at the relationship between here and here. Okay? Yeah. So that's the point, right? Yeah. Okay. So, and the second thing is, okay, so this is basically the right moment to introduce another concept now. We introduce a concept called star Laplace transform. Okay, star Laplace transform. It's nothing new really. Basically this y star of s, right, or x star of s, and that's the star Laplace transform, what it's basically referring to at here. Okay, yeah. So let me rewrite that expression when I talk about the sampling theorem. The connection between the original at Laplace and star Laplace is this expression. Okay. So this is your connection between original x of s and x star of s. And you can literally change this symbol x to any symbols. Okay, so that basically functions as a definition for this so-called star Laplace transform. All right, yeah. So you give in any s function, you place the y here. Then what's that y star? Then the same thing. Okay, yeah. So as I said, you can take a look at page 146 for details of this. Okay, yeah. Now let's go back to this simple block right here. Okay, by following the flow of the signals. All right. So the signals from here to here, x star, and from here through the h, you got y of s. So the flow of the signals will give me the output y of s at here equal to what? The input signal times this block at here, right? So basically that give me h of s times x star of s. Okay, x star of s. Okay. Is that good? Okay. Now bear in mind, I'm trying to derive a pulse transfer function. And I said pulse transfer function is about the ratio between two discrete signals, right? So far the way I write here, there is nowhere to show the relationship between the ratio between the two discrete signals. You have a discrete here, but this is still not discrete yet, right? This is still y of s. And what's discrete here? This one here is representing, that's the discrete one there, right? So the idea is I want to obtain what is the y star of s, right? Y star of s here. So this is actually a more generic operation now. So if I apply trying to get from here to here, right? Get from here to here. So what do we do? It's like you do this. Yeah, you basically let me move this down a little bit here, okay? So move down a little bit here. Okay. You basically you can call it, this is, let's apply this is so-called star Laplace transform. Okay, let's apply this operation. Let's apply this operation to both sides. Okay, to both sides. It's like applying a derivative to both sides. Okay, or applying an integral to both sides. Okay, yeah. So the left side just there's only one expression, so whatever the operation, you end up with just y star of s, right? The right side here, so literally what we should do before we move ahead, we should maybe think about this. This is basically what happens at here, right? You apply a star Laplace transform operation to the right side, okay? To the right side. Good? Okay. So, and what is the star Laplace transform? As I said, this is the operation, right? This is the operation. You can literally change this x to any symbols you want, right? To any symbols. So in this case, what do we change this x here? We're going to change our x to what? To this h x star. Okay? Yeah. So I'm going to follow closely with this operation here, okay? Closely, which means, so what do I change? I will replace the x with h and x star. So here is what happened. H, still h here, the s becomes that. And then x, right? This is x star here. Okay, yeah. So that's from here to here by following this so-called star Laplace transform. Okay, yeah. So the x itself has replaced by this and that. Okay. Yeah. Okay. So from here, now we're gonna actually move forward. Okay. By stating another property at here. Okay. Before we move forward, so let me list a property at here. Okay. So the property to list at here is your x star of s. Okay. So x star of s is periodic. Okay. This x star of s is a periodic function. So what does a periodic function mean? So basically means whenever you change this s by g omega s k, okay, it's basically repeating itself. So that's basically what periodic function means. Okay. You can actually think about that drawing I just sketched there, right? So this x star of s, if you think about the drawing that we draw it here, right? So it's a periodic function, it's repeating itself, right? So this one here, essentially what it means by periodic at here, okay, it's just repeating at intervals of omega s at here. So what does that mean is, if you're coming back to this y star of here, what does it mean is, then this second term, right, this term here, x star here, and that basically is what? X star of s, right? That's basically x star of s, because it's periodic. Okay? This property at here, okay? It's periodic. So now, this y star of s, okay? This y star of s, okay? Let's look at the right side again. Now this is a periodic, so this is x star of s, so the k term is gone, right? It has nothing to do with the k anymore. So you can literally take this out of that summation sign. So that basically become 1 times capital T x star of s, and then the rest of the summations. Okay, the rest summations. Good? Yeah. Second observation here. If I look at this summation at here, now what is this thing here? This summation h of s plus g omega s. If you look at this whole thing at here, what is this? Exactly, right? Of course there's a 1 over t, but it's t times h star of s, right? Yeah. So basically, this term here is a t times h star of s here. That's your star operation definition, right? Yeah. Yeah, that's right. So now we can just get rid of this. So altogether it's x of s times h star of s, right? Star of s. Okay. Yeah. So for now, you may think this is absolutely horrible. You know, why are we doing this in here, right? Unfortunately, I had to explain this. But this is a simple case. You need this to build up a more sophisticated block when you have a block there. Okay. So now everything on both sides of the equation here, it's all star, 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 right? Everything is star. When you have everything is star, remember what we do? We can replace the s with 1 over t ln z, and we can get y of z equal to x of z, h of z, right? So basically you get a pulse transfer function which is between the y of z and x of z. Okay? Yeah. And that, in this case, it's equal to the h of z. Okay? In this case, it's equal to the h of z here. Okay? I'll show you some examples, okay, to really to put things together, to look at the connections among the different concepts here. Okay. Yeah. So this is basically your PTF, right? This is your PTF. Okay. For this block, for this block, because the blocks are if different from this, is you might actually have a different expression, right? Yeah. Then you could extend this expression slightly, just so this h of z. You might ask this, so where is this h of z from, right? How do I get to this h of z? This h of z, okay, literally just in this case, just the z transform of your original h of s. Okay, yeah. Okay. And we have to have an actual h of s in order to get this h of z. I'll give you a few examples, maybe next lecture, but just a warm up. And this is how you would be able to obtain your h of z. This is actually one method. Okay, yeah. So let me give you another example here. Okay. So in this case here, I will slightly modify the simple block I was just using. Okay, so let's say the block is modified, okay, slightly. Slightly basically means instead of just one h of s, and I inserted additional block, which is g of s here. Okay, so the two blocks connected in series. Okay, so let's ask the same question: what is the pulse transfer function between y of z and x of z? Right? Okay. Now this time, I'm going to actually make use of the results of some of the derivations from previous steps here, okay, to derive this pulse transfer function. So, but I will start from the very beginning, basically by following the flow of the signals. The signals flowing through here, right? Flowing through here. So here's my output y of s. So y of s equal to what type of flow? Equal to the signal at here, which is x star of s. Okay, going through this g of s, going through the h of s. So basically, you have a h of s, g of s, and then x star of s. Okay, yeah. Make sense? Yeah. So. And now I wanted to obtain this, right? So I will apply the start Laplace transform operation to both sides of this equation. Okay, to both sides of this equation here. By applying this, basically the right side, okay, this is what's going to happen, right? Yeah, it's like you're taking derivative on the right side, but in this kind you're taking a star Laplace transform. Okay. Okay. So from here to here, okay, I want you, okay, if you're really interested here, to follow this star Laplace transform. This is a transform here, isn't it? Right? This is a transform. Okay. By following this definition, you can try this. By following the definition here, here is what's inside the block here, right? How would you follow that to get the results here? Okay. But the point here is, okay, the pitfall here is, usually if you follow closely, you get the right results. But there is a very typical mistake, okay? Especially when I say this is an operation, there's a very common mistake. Okay, so here's the operation. It's like let's say taking, I don't know what would be equivalent to one. Maybe taking derivative. Then you say, okay, I'm going to take a derivative of this, time derivative of this, then time the derivative of this, right? It's like that type of concept, right? So there's a very common mistake is when you look at the start operation of this, you say, okay, so that must equal to G star of S, H star of S, and then X star of S, again star, right? Yeah. So star is already starred, and you take another star, it doesn't change at all. Okay? Yeah. So this one here is still X star of S. But this is a mistake. Okay? This is a very common mistake here. The operation doesn't really work like this. When you have an expression inside this big bracket and you're taking the star Laplace transform, what you have to do is you have to multiply these two together first. Okay? Multiply the two together first to make it one single S function. Okay? One single S function. And then the result is you apply the star to this single GH set here. That's your star Laplace transform. Okay? Yeah. So remember that pitfall here, okay? It's not G star, H star, it's multiplied together to get a GH star. It's basically like you combining the two blocks together, make it a GH block first. Okay? Yeah. Then you take the star Laplace transform. So overall, by replacing the S with 1 over Z, ln Z, you get your Laplace transform function in this case. Okay, so it's GHZ. Okay, so that basically GHZ is a Z transform in this case, like that. Okay. Okay? Yeah. So I'll show you a simple example now, okay? Just a very simple example, and just to explain basically how from, for example, from here or from here to get the final pulse transfer function, okay? And you have actual blocks. So let's look at an example here. So let's say I'm dealing with a block like this, okay? Suppose this is a block we're dealing with here. Okay. And that's a simple block. This is, you can consider this is H of S at here. And here's input X, and here's output Y, right? Yeah. So as we just derived, and what's the pulse transfer function if I'm interested? It's what? H of Z, right? Which is a Z transform for this 1 over S plus A. Okay? Yeah. Is that good? Yeah. So how do I go from here to here then? Use the Z transformation table. If you look at the Z transformation table, okay, so looking at the most left side, you have 1 over S plus A, right? And then go to the last column here, which is this. So in this case, that basically equal to Z, okay, like that. Yeah. That makes sense, right? So now you can actually think, even without giving an example here, if this H of S is not so simple as 1 over S plus A. For example, if H of S maybe is S plus A, S plus B, like that, right? So how do I go about to get H of Z? So we have to do what? Partial fraction expansion, right? Yeah. For this guy here, okay? Yeah. Then you use a table to get here, okay? Yeah. So that's one example, right? Let's try. Let's see. Let's look at the next example. Let's see if we can finish here. Okay. Another example here. This is more or less. Let's see. Okay. Maybe I should write down. Okay, so so let's say this is another example here, and this is actually I will summarize. This is essentially a typical example of a so-called open loop. Okay, open loop pulse transfer function. So this essentially falls into this kind of schematic, right? You have two blocks at it here. Okay, two blocks. Now here is zero order hold, and here is, let's say for example, this is a plant. Okay, G of S. Okay, and overall it's more or less like the previous example, just one single block if you put these two together, right? And zero order hold, as we just derived, its transfer function is 1 minus e to the power negative ts over s, right? Yeah. And let's call the whole thing in here. Let's call this two blocks together. Let's call it P of S. Okay, let's call it P of S for the two blocks together. So now, as we derived, you see the results set here, right? Your pulse transfer function is equal to Z, okay, and because all together call it P, right? So P of S. Okay, so basically it's equal to the Z transform of this P of S. And Z transform P of S, in this case, it's a zero order hold time G of S. Okay. So I think I might as well just stop here. Okay, we'll finish this example in the next lecture. So I got to run to my next lecture. Any questions? All good? Okay. Yes. Post what? Oh yeah, sure, yeah.